the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 91, where today, once again, we have special guest Dr. Zack Wolske, a postdoctoral fellow here at the University of Toronto. So, Zack, you want to say hi to our audience once again?
Yeah, hi, everybody. Thanks for having me back.
Of course,
Yeah, no
wonderful
problem.
to have you here. I mean, I think it was a great reaction, that episode, from our audience, because I think they also saw that that was the one episode where we actually learned things on the episode, and we were like figuring things out on the episode, and it was.
Oh, I'm sure you've learned things on the other episodes.
Oh, for sure.
Of course. What I mean is, like, we were figuring things out like hands-on.
Yeah.
And it was very nice having kind of like almost a one-on-one professor experience.
Yeah, it was much more interactive.
Yeah, the first time, I think it was only because it was in person.
Yeah, it was our first in-person
I
one.
think that's why, because it was our first in-person guest episode. It was just so much more interactive. Hopefully we can have future ones. But as you all may know, due to the new variant of this current pandemic, we have gone back to a little bit online. So we have Zack here on Zoom with us once again. So
You get to see me with glasses on?
for the first time. So very excited.
Quickly,
Okay,
before
quick
we
news,
get
quick news.
into the episode, we are now at almost 350,000 downloads. Thank you to
Wow.
everybody who's been listening to the podcast. We are this week actually we hit 20,000 followers on Spotify.
Oh, that
Thank
was a
you,
big
everybody.
moment. Yeah, we put it all over our social.
Yeah.
So everyone is very excited.
If you want to keep up with all of the updates, make sure to go to our Instagram at math.physics.podcast. And finally, for the comment of the week, it goes to Upendra. They say, "Hey, love from India. Been listening to you guys from the start.
Oh.
Love how y'all have grown. The way you guys discuss topics makes me feel like I'm sitting with friends. Super fun to listen to. Do continue making great content."
Oh.
Thank you so much for
Wow.
that comment.
What a
And
comment.
if you want to be next week's comment of the week, go to this YouTube video and comment underneath it, and you might
Super
get
simple.
picked.
So yeah, wherever you're listening to it, just hop on YouTube, check it out, check out our faces, and if not, just give that audio a follow.
Yeah.
Yeah, let's get into it. So today's main topic, or I think we're just freestyling it here this time, but is gonna be a little more in depth, because last time, while we were kind of talking about a little bit about you, a little bit about how you got into the field of math, today we can just go all into your field itself. Just go all into what makes math wonderful, and why do you like to count numbers? That's the best way to put it.
Sure. So this topic is combinatorics, right? Which is like a fancy math way of saying counting stuff. And I love it. It's one of my favorites. It's not really my research area, but it comes up in all kinds of research in any field of math. We always want to know, can we turn it into something finite and then just count? And that will tell us something. It's
I
also
guess-
maybe like the oldest math that like people have been counting for a long time. And every society that we know of counts stuff.
I guess also with the idea of the limit, we also have a lot of advantages to finite counting nowadays, right? Because like if we can represent anything infinite with a finite variable, it goes to n, and then just represent the same system in a finite way, with our understanding of like infinities and limits, we can apply our finite counting ideas to infinite counting ideas.
But how would the system be infinite in the first place if you can make it finite?
No, I'm saying instead, if let's say it goes off to infinity, I'm saying take the same thing to n, make the system for n,
Okay, yeah.
and then take n to infinity. So like that's another advantage of having the fact that, hey, these all, like the fact that we can count these numbers, like you can kind of switch between finite and infinite pretty easily. Was that kind of what you were going on, or was there something else that you were talking about where you were talking about the switch between the two?
I mean, I guess I never really think about infinite things. So I shouldn't say that. In combinatorics, we don't really think about infinite things. We would say there's just some finite number of things that can happen, and maybe we can count them all. And a lot of computations are done like this, right? If you ask Wolfram Alpha, give me a limit as something goes to infinity, it doesn't actually do that.
Mm-hmm.
It comes up with some finite way of approximating it, and then it tells you that number. So like if you integrate, like a Riemann integral, something between 0 and 1, and we want to know all the values of the function, we don't actually do an infinite thing. We just make n big.
Mm-hmm.
And we say if it's big enough, it's pretty close. And then we tell the approximation.
But what about this? Can you, like, when in like upper level combinatorics, do you ever look at problems that become continuous and ask about like how many ways can this like continuous thing happen? Like, for example, if you're throwing darts at a dartboard, you can say like how many possible like things can I hit even though that it's not discrete?
Absolutely. We have ways to sort of model probability based on a uniform distribution, uniform with respect to area. So we would say if we have a certain area that we might hit and we section it off into equally sized wedges, we should be equally likely to hit each of those wedges. Or if there's a very small bullseye, the probability of landing there should relate to the area of the bullseye compared to the total area.
Right. But you can't really say anything about an individual shot.
Well, I would say like even in the case where we're pretending that there's an infinite number of possible points that we could hit, there aren't. Like the physical reality of atoms is that there's some finite number of things that are in there.
Also, like if we're getting that specific, then like even the tip would take up like quite a few hundred atoms, if not quite a few 100,000 atoms.
Okay.
So then like, you know, we would be subtracting it from there.
So I guess you're counting like the area of the tip of the dart in terms of like square atoms.
Square atoms. I guess that would be one metric to use, right, for probability. Because I mean, I guess so if you're trying to model something like that into a probabilistic nature, like I guess everything at the end of the day can be seen as some sort of, because I guess at the end of the day, if you just take the full area, like let's say the area of the circle is like 5 square centimeters. Wait, what like the the probability of like hitting one specific area would be like, I mean, if it's all uniform, if we're assuming it's all uniform, obviously in a dartboard it's not. I'm assuming some are harder than others, but I'm saying like assuming a uniform distribution here, it would just be 1/5 in this case, right?
Well,
so if we have a little bullseye that has area 1 and the total area is 5, then absolutely, it should be like 1/5.
Yeah. So I mean, it would be a pretty straightforward, just a area calculation.
Yeah.
I guess.
Yeah. Exactly.
I guess so.
So combinatorics lets us do all kinds of different counting related things. And in like life, you might see it in terms of games, things like playing cards. If you look at a deck of cards, what's the probability that certain things will be dealt? And the way to deal with that is usually count up what's the total number of ways it can happen and what's the total options available, and then divide those things. So it's a really nice way to turn some kind of more abstract probability idea into something very concrete and something that like we can get a computer to count how many ways are there to do this.
Is that not even how a computer computes a lot of these things, just by sheer counting the number of processes taken or counting the number of ways? Because I think sometimes, especially for a computer to do certain algorithms, it's just easier. Just count it. know?
Absolutely.
Especially because it can.
And we might say that like this is like a brute force method. We just count them all up. And if you ask a computer to integrate some function on some interval, it will break it up into some number of pieces and then add up all the values and then tell you that number. And generally, if the number of pieces is big enough, that number is close to what you would get sort of algebraically through your rules of integration.
So
Oh, is that really?
I didn't know computers did
yeah,
that
I didn't
numerically.
actually-
I
I
thought
didn't actually know
computers
that.
did it just like because it knows how to integrate.
I don't.
It does not know how to integrate.
Okay.
Because I guess
There
it
are certain,
converts
depending on
everything
depending on how it's implemented, it might say, okay, if you get this polynomial, do this rule. If you get a trig function, do this rule. But if you plug in some kind of combination of polynomial, trig, exponential things that's kind of weird, it numerically evaluates.
Wow, that's pretty powerful. I mean, I guess it's a computer. But
Yeah, I can do that.
it can. But
So
I'm saying it's pretty
a
powerful.
problem that we come up with when we're trying to get this done by like brute force methods is that the number of things that we might need to count grows way too fast. That if we say, computer, please count everything, it can come back and say, this will take 1 billion years. And I say, oh, I needed it
error.
like now.
Yeah.
So then a lot of our work in combinatorics is to reduce the number of cases that we need to check, or somehow do like a clever counting so that we don't need to brute force do everything, that we can get all possible cases without spending 1 billion years enumerating all of them.
So what would be like an example of one of these things that just can't be computed? Or well, it can, but just takes a really long
something
time.
as easy as 52 factorial. Don't you know
Absolutely.
about that whole thing?
Oh, you can't do that?
No,
Oh.
you cannot. Computing, so like the whole thing is like, because 52 is like the number of cards in a deck, so it's like a famous number. So the whole thing is the whole.
Wait, so 52 factorial represents, can you tell me? Or what do you mean by 52
Yeah, so it's the
factorial?
amount of ways you can
Oh,
permute, right?
So it's the amount of different ways that that you can get of each card, basically, from a freshly shuffled or from a brand.
So
new
I have
card,
like a full
freshly
deck of
shuffled
cards. I
Yeah.
can move them around in 52 factorial ways. So that after
Nice.
shuffling,
Concise
there
way
is
to say it.
some order to the cards. And you're saying there's 52 factorial different ways that can happen. And this 52 factorial is like 52 times 51 times 50 all the way down to times 2 times 1.
I mean, just like with permutations, like if you just think of each card as a separate, I wouldn't say event, but like as a separate card in this case, because they are independent in this case, like you would have this card having a 1/52 chance of being this. And then the next card can't be this one anymore, so it has a 1/51 chance of being this. And then the next one is 1/50, 1/49. So then you just keep multiplying. So the idea is the probability that you get this one card out of your 52.
Or this one ordering.
Is this one order out of your 52 is 1/52 factorial, which is the idea behind it.
So how big is this number 52 factorial? It's
Pretty
Because
big.
it seems like
I watched a crazy video on it. Like, there's a really cool video on the immense idea of 52 factorial because.
Do you want to link to it in your description?
I don't even think we mentioned it last time, but we didn't put a link last time. We forgot. Again, we mentioned something. We forgot to put a link.
Yeah,
we always
we'll-
forget.
we'll put a
Please
link.
remind us.
We'll put
Remind
a
us if we forget, but we will do it. There's a really cool, very popular video on the nature of 52 factorial and how big this number really is. And he basically kind of like also like talks about how human brains just can't, number one, comprehend these large scale numbers really, like, you know, like 1 million seconds versus 1 billion seconds, you know, that common thing, right? And that's why you may have also heard somewhere that this pair of cards that you see in your hand is possibly the only pair of cards that's ever been dealt.
A pair?
Or like
two?
But you know that idea, right? Like this order of cards in your hand is like possibly one
like
of
the
the
whole
only
deck,
orders
right?
that is ever existed
Yeah.
because of the sheer number of 52 factorial.
So like, let's pick a game where you deal out all the cards.
Mm-hmm.
Like if you're old, then like bridge, or if you're young, then any of the games where you deal all the cards and you're trying to get rid of all the
President or
cards in your
something like
hand.
President, I
I
guess.
don't know.
President.
President? Okay,
Kind
yeah.
of.
I was trying to think, what's a nice way to say the name
President.
of this game that I know of differently?
President is a very.
So any game like that, there's 52 factorial ways to give all the cards out in some order.
Right.
But
Exactly.
if you get 13 cards in your hand, you don't care what order they came in.
So it's only a
Right.
combination, of course. It's not a permutation in this case.
So
Yeah.
there's fewer ways to deal them all out.
Of course. It's like the same example about 5 people come in a club, they give all their jackets to the bouncer. When they come out, what's the probability that each of them got a jacket? Second question, what's the probability that each of them got their own jacket? So what's the probability that each of them got a jacket? Well, 5 choose 5. That's 1, because everyone obviously got a jacket, because 5 people came in, 5 people came
Wait,
out.
5 choose 5?
Yeah, right, because they're 5
Right,
people.
that's 1.
But in this case, if you are saying what's the probability that each of them got their own jacket, then you're asking about a permutation. So you're asking 5 permute 5, which is now 120, which is 1 over 120 chance that each of them got their own jacket. Right. So like I like that.
That was a
that's
lot all at once. Can
Sorry,
I ask some
mean-
questions?
Sorry, that's like a famous. I don't know if it's very famous. I guess
Famous
it's
to
famous
you,
in my
maybe.
probability
Yeah,
class.
I've
It's
never
very
heard of
famous in my
that.
probability class. It's like an idea to understand.
So you have a
combinations
situation,
versus
5 people
permutations.
have like put something somewhere and then they come and pick up a random one.
Mm-hmm.
Basically.
Okay. And everybody gets 1 jacket back. But you want to know what's the probability that they each got their own jacket.
Exactly.
Okay. And you're saying this is 1 out of 120?
Because it would be, in this case, it would be 5 factorial, right? Because it would be a permutation in this case. Because each of their jackets, because the question, sorry, wasn't what's the probability that one of you will get your own jacket? I don't know if I ordered that correctly. The question was,
No, you
what's
said
the
everyone.
probability that each, yeah, exactly, everyone will get their own jacket. So in that case, what's the probability that this guy gets his jacket? 1 over 5. What's the probability that this guy gets his jacket and this guy gets his jacket? 1 over 5 times 1 over 4, because there are only 4 jackets left. And then times 1 over 3 times 1 over 2 times. So that's 1 over 120.
Okay. Interesting.
Right.
What do you think about the one where, what's the probability that you mentioned where someone gets their own jacket, but maybe not everybody?
Yeah, so in that case, that's a simple combination, right? Because in that case, you're just saying, okay, everyone, there are 5 people and there are 5 jackets.
Wait, no, this is more complicated because, like, what's the probability that at least one person gets their own jacket?
That's not what the question was, but you can make it more complicated with that, sure.
What was the question then?
So the first idea is basically what's the probability that each of them get a jacket? Because in a case where, let's say, 4 people come in with 5 jackets, there's actually a probability that not all of them do, right? Because like then 5 choose 4, because there are only 4 people. Or sorry, 4 people come in with 5 people come in with 4 jackets. Sorry, is what I meant. 5 people come in with 4 jackets.
Oh,
Then not
somebody's gonna
everyone
be
will
cold.
have a jacket, right?
Okay.
Exactly. But in this case, because 5 people are coming in with 5, the question is, well, what's the probability that each of them will get a jacket? Well, it's 1, because there are only 5 people to give out 5 jackets to. But in a case where each of them will get their own, that's when you add that thing. But obviously, if you want to make it a little more complicated, you can then say, now you're asking, what's the probability that at least one of them got their jacket,
Yeah.
right? What's the
What's
probability?
this probability?
I have no idea.
That well, no, we can think. What's the probability that at least one got his jacket? What that means is, what's the probability that 1 minus no one got their jacket? Is basically what you're saying,
Yeah.
right?
Yeah.
So what's the probability that no one gets their jacket?
That's still kind of hard to,
What's the probability?
because there are a lot of options,
that
right?
no one gets their jacket. So in this case, each individual, again, you can just count because these are all just counting things. Like there are only 5 people here. So in this case, what's the probability that none of them get their own jackets? So person A, one of his jackets.
Oh, then there's a 1 out of
Would it just be one
There's
minus?
there's a 3 out of 5 or 4 out of 5
Oh, it would just be one minus, right? Because 4 out of 5 that he won't get his jacket.
Yeah.
Oh yeah, exactly. You're right. No, exactly. You're right. So it's a 4 out of 5 that he won't get his jacket, right? And then for the other dude, it would be a 1/4 that he would. So it would be a 3 out. So it would be a 3 out of 4, and then it would just.
Well,
it
wait.
would just, so it'll be so it'll be 4 factorial over 5 factorial. So it'll be 1/5.
Well, hold on a second. If the first person picks the second person's jacket,
Oh, then that blocks off the whole rest, right?
it changes
Yeah.
the likelihood that the second person can get their own
Yeah.
jacket, right?
Yeah, because if I pick your jacket, then the probability that you get your jacket is 0. And if you pick the next person's jacket, then the next person has a probability of 0 of picking their own jacket. So it changes. This is kind of complicated.
It is complicated.
Yeah.
This is in a topic that we would call a derangement. So I was just showing, like, if I picked 5 different numbered cards and then I like shuffle them around, I'm asking, what's the probability? The shuffling is like that people are going to randomly pick a jacket.
Mhm.
What's the probability that the first one is not a 1? Okay, so right away the first person got their own jacket. And the probability that the first one is not a 1, and the second one is not a 2, and the third one is not a 3, and the fourth one is not a 4, and the fifth one is not a 5, all together. So we could write down all 120 ways that there are to arrange 5 things, and then just cancel the ones that have like a 1 in position 1 and a 2 in position 2.
No, but would it not be 1/5 at the end of it though?
No, it's more complicated.
No, because
Would it be? So it might, like a lot of things in combinatorics do end up with, it seems very complicated, but then somehow everything cancels out, and there is just the probability that you might expect.
Oh.
Like I'm pretty sure my thinking was correct. Cause like,
Well, you weren't considering one thing.
no, I know. I
Well, we
wasn't
can try. Let's
considering
try
the
with
fact
smaller
that-
numbers.
Yeah,
right?
yeah.
Yeah,
That's
okay.
what-
I know. That's always easier.
Like, what if there were 2 people?
What's the probability that at least one of them gets his jacket in this case? So what's the probability?
Oh,
that
well,
none of
this
them
is
get their
just
jacket?
this is just 1 out of 2, right? Because there's a 50% chance that
Yeah.
that you both get your jacket
Yeah.
and 50% chance that you don't.
Yeah,
So
exactly.
Okay.
Exactly.
What if there were 3 people?
Yeah, and 3 people.
oh, now it's like there's
It's a 2/3%. It's a 2/3 that you.
no, it's more than that because one possibility is that all 3 of you get your jacket,
Yeah.
and then there are 3 possibilities that like first person gets his jacket, other 2 don't. Multiply that by 2 because don't
No, but
multiply
you're doing
that
a
by 2
permutation
because
right now. You're just doing a manual permutation. Is what you're doing in your head. You're just doing a 3,
I know, but I think
3 times 2 times 1.
I think it's
Because there's 6 total ways for them to get their jackets. Right? There's 6 total ways for them to get their
I want to hear what you have to say.
Okay, yeah, just continue.
No, I mean, I like this. There's 6 total ways.
Yeah,
So
okay.
let's, you can check them all, right?
So yeah, exactly. That's what I was saying is that there's one possible way where all 3 get their jackets, and then if all 3 like now the only other case other than all 3 not getting their jackets is 1 gets their jacket, because if 1 gets their jacket and the other one doesn't, then that automatically means that we're not in the first default case where all of them do get their jackets.
So you're saying you can't have exactly 2 people get their jacket,
Yeah,
and
exactly.
the third one doesn't.
Exactly.
That there's really, like, it seems like there should be 4 cases.
Yeah.
Everybody gets it, all 3,
Yeah.
or 2, or 1, or 0.
Yeah.
But the case of exactly 2 doesn't happen.
No, wait, sorry. That's not what I
If
was
2 people got their jacket, the third one also gets their jacket.
Yeah, but what I was saying is that either all 3 get their jacket, or the first person gets their jacket, the second person gets their jacket, and the third person, like those are 3 separate cases. So there's 4 cases out of 6.
Out of 6 total.
Yeah.
Okay. So you're saying the ones that we care about, everybody gets their jacket back, or 1 person does and 2 other people switched.
Yeah.
And there's 3 ways for that to happen.
Yeah.
You pick the 1 person who gets their own jacket, and then you switch the other 2 people.
Yeah.
So there's 4 options where somebody gets their jacket back out of 6. Does that match with
No.
Wait,
your one out of?
are there 6 ways? There's 1, 2,
Yeah.
3, 4, 5. There's 5 different ways.
How? What do you mean? 3 factorial. You have 3
Then-
people.
Because what I'm thinking about is like either they all get their jackets.
So you're thinking
They
about
don't.
it manually, and the problem is you don't have a piece of paper in front of you.
Okay.
That's your problem.
Oh no,
So-
I mean I think this is fine.
No,
But,
like, you
in the
but
case,
no,
okay,
the
you're
thing is,
saying
especially with like 3 people, like I guess 3 is okay because there's only 6, but like
Yeah.
you get the 4 and it immediately shoots up, right? So it's gonna
Yeah.
continue to shoot up.
wait,
So
Ray,
like, you
let's
just-
analyze
yeah.
this one of what are the 5 options? Everybody gets their jackets.
Yeah.
The first person gets theirs and the other 2 don't. The
Mhm.
second and the other 2 don't. The third and the other 2 don't. Or no one does.
Yeah.
How many ways can that no one gets their own jacket happen?
Just one way.
No, why?
Why is that?
Because imagine none of them have their jackets. If any 2 people switch, then one of them is gonna at least get their jacket, right? Is that not true?
That might be true, but why does that make it only one way?
Because if you switch anybody's, then it automatically becomes a case where one of them has their jacket.
Sure.
What if it's the middle? No, because then these guys would just switch and they would have each other's. What if one?
Like
would
if
have
one
this?
has 2, 2 has
Yeah, there
3,
would
and
only
3
be
has
one way. There
1.
would only be one
If
way.
you switch any 2 people, then now we're no longer in the case where all 3 of them don't have their jackets.
So if one has 2,
Yeah.
and 2 has 3, and 3 has 1,
Yeah.
that's one way it can happen, right?
Yeah.
But what about this?
Oh,
way?
wait. That's true. That's true. You can just rotate all of them around by 1. So there's only 2 ways then.
So
Wait.
this question, these are what are called derangements.
Yeah.
Some way of arranging the numbers from 1 up to something, up to n, where each position doesn't have its own number. So I would say there's exactly 1 derangement of 2 numbers,
Mm-hmm.
and then there's 2 derangements of 3 numbers. I can either go 2, 2, 3, 1, or I can go 3, 1, 2.
Right.
So what we want to know is how many derangements are there? If you had 5 numbers, how many ways are there to put the numbers 1, 2, 3, 4, 5 in a row so that position 1 is not 1, position 2 is not 2, position 3 is not 3, and 4 is not 4, and 5 is not 5?
Would that be like n minus 1?
Would it be n minus 1?
Because I'm thinking
So far we know 2 examples, and so far it's always been n minus 1.
Oh wait. Oh no. If the number gets bigger, then it's no longer n minus 1.
There's no way it can just be.
Because you can have them like arranged in a circle,
But
and you can cycle n minus 1 times, but then at any one cycle you can like switch 2 of them, and it would still be because we have more than 3.
yeah, but in the 5 case too, like we can just do them individually, right? Like like the first one doesn't is not 5, is 4 over 5. The second one is not 2, is this. The third one is, and then you can just multiply them through. Like that's how I got my original 4 over 5 factorial, but like that seemed like you said no. So that's why I'm thinking still.
I don't think that works.
So
Because
it gets
we
very
just-
complicated.
Yeah.
Right?
Yep.
And this is what I love in combinatorics. You can have some kind of easy question, and it's also very easy to check small cases. But as soon as n gets a little bit big, we need to know what are actual patterns that are happening. And I don't want to enumerate. I don't want to write down a list of all 120 ways to put 5 things in a row. And if there were like 10 people, or 52, what happens in a deck of 52? What if I numbered all the cards from 1 to 52, and I said, let's play a game. I'm going to flip over a card and say the number 1 or 2 or 3, whatever one I flipped, and I win if I flip over a number that I say.
Ooh.
And I lose if that never happens. What do you think my probability of winning is?
Probably
if
low.
if you say number, like just number.
Yeah, just numbered. Like
Wait, no,
I'm
it's
gonna
high then.
I'm gonna
'cause they're-
pretend that they're all
'cause they're
distinct.
13.
So
Oh, like
maybe
they're-
what I'll do
they're
is
all
I'll say
distinct
like
numbers, like 1 to 52.
I'll say each
Oh, okay,
card
okay,
once.
okay.
Like I'll
Okay.
say ace of spades, two of
Yeah, I
spades,
get it,
three
I
of
get it,
spades,
okay.
four of
Okay.
spades.
I think
and
you
if I
have a
ever
high
flip over the
chance.
one that I say, yeah, how high?
Pretty high, because we were just like, it seems somewhat countable to find the cases where you don't end up naming.
But the
one of
question was,
cards.
he does.
I know he does, so that means your chances of winning are high. Because the odds that you don't do it are, like, you can just count them almost. You know, I'm not saying you when you have 52 cards, you can just count them all, but I'm saying it's
No, but I'm saying, like, he wins if he
If he
guesses the
does.
card that he gets up.
no, he's not guessing. He's just naming numbers 1 to 52, like, in order. And if
This is like if people checked their coats, what's the probability somebody gets their coat back?
Yeah.
At least one person.
Oh, okay.
Or
it's
I
like a
lose
1
if
minus
nobody gets their coat back.
Yeah.
And it's that 1 minus nobody. So if nobody is really small, then 1 minus this will be really big, kind of thing. So in this case, if you get none of them right, you were saying what? That it's really small. What were you saying?
I'm saying that he has a high chance of winning the game.
How high?
I don't know how high, though.
Would you say like over 90%?
Yes.
Okay.
Because, like, I think the higher the number of coats or cards, then the higher chance you have of winning.
Okay. So I have some interesting information for you.
Uh,
If I go between like 52 and 100,
yeah.
my probability of winning is basically the same.
But it
For
gets,
both of those games.
It gets a little bit higher, though, no?
It alternates.
Oh, what? What? That's surprising.
It does a thing of going above and then going below and then going above and
Oh.
going below. So if I picked 53, now I'm going to have to try to figure out which one is lower and which one is higher. I
Wait.
guess I can figure it out from the cases of 2 and 3.
Is it just odd even?
For 2, I have 50% chance to win. For 3, I have a 66% chance to win.
Yeah.
But then for 4, it goes back down.
Oh.
So on odd numbers, I have slightly more, and
Yeah.
on even numbers, I have slightly less. But they both get very close to a certain probability.
What is it?
Well, I mean, this will be for you to investigate.
Oh, man.
Imagine it was the golden ratio.
These are called derangements.
That would be really cool.
So
though.
you can find them. And it is very cool what number you get out of it.
Oh, man. Okay.
And
I'm
I
gonna
think
search this
cooler
up.
than the golden ratio.
Oh, it's cooler than the golden ratio. I mean, I have an iPad in front of me. I can search this up. This sounds really cool.
These are the types of things that we would talk about in combinatorics, and also the types of things that show up in terms of like your estimates of probability are not necessarily accurate, right? This is how like gambling is a big industry. There are games of chance that we can set up where the initial guesses of what the likelihood of something happening is are not exactly what they are.
Right.
One of the oldest games that we have that's been like analyzed probabilistically, and one of the foundational things that we have from like modern combinatorics is about throwing dice. So if you roll a 6-sided die, you can play a game where someone says, okay, take 4 rolls. If you get a 6, if you get at least one 6, you win. If you get no 6s out of all 4, you lose. What do you think the probability is that you win this game?
So if you get at least 1 6, you win.
Mm-hmm.
And you have 2 die every time you throw?
No, you get 1.
Oh, 1?
So you get one thing 4 times. We're going to do 2 next. 2 is the
okay.
hard part.
Okay, so I think what? Yeah, we'll do it. So what I was thinking is that you have a 1 out of 6 plus 1 out of 6 plus 1 out of 6, yeah. So you have a high chance of rolling a 6.
Now you're saying 1 out of 6 plus 1 out of 6 because you can get a 6 on the first roll, or
Yeah.
the second roll, or the third roll.
Yeah, so
But
you have 4 out of 6.
some of those both happen.
Oh, so you have even more chances. Wait.
We have to subtract the ones where they both happen.
Wait, what do
Imagine
you-
if you rolled 2 dice. You can
Yeah.
get a 1 out of 6 chance that it's a 6 on the first one, or 1 out of 6 that it's a 6 on the second one, but you've overcounted because there might be a 6 on both.
But we're throwing the dice like one at a time, right?
Mm-hmm.
So
Wait, they're independent events though. Why would we have to subtract a?
Well, what happens if we did it 6 times? Are you saying it's always going to happen? What happens if you rolled it 7 times?
Okay, yeah. No, you're right. You're right. You can't just add them together.
Okay, so suppose somebody wanted to know more about combinatorics. Where might they go?
Well, funny you might ask, but you can actually head over to brilliant.org. They have puzzles of the day all the time, where each day you get a different new like math puzzle / logic, even combinatorics related. And we even tried them out before starting the podcast, and I might say they were very, very interesting. Rehan and I both got caught by the problems. They're all multiple choice, and sometimes it's not the most obvious choice. If you want to learn more about combinatorics, make sure to check out the contest math courses, where you can do a whole lot of problems on these counting problems.
Yeah, and interestingly enough, they also have a really cool course on derangements. So they actually talk about derangements on Brilliant. So if you found anything that we were just talking about really cool, I mean, go check it out, because that's actually what I was just now reading while I wanted to talk about it. So go check it out. Link in the description below if you want to go ahead, just type, what is it? Brilliant.org/MPP to get that 20% discount off your premium subscription. So yeah, just go click the link in the description below and enjoy.
Boom.
So yeah, so rolling 2 dice now, right?
Did we get to 2 dice?
Yeah, let's
I
say
think we're
you
at 2
rolled
dice, are we
2.
not? Well, yeah, we're at rolling 2 dice now.
And I want to know, okay, how likely are you to get at least 1 6? And I'm saying it's less than 1 6 plus 1 6.
Out of 4 tries.
So let's look at 2 first. But how about 4? Or how about, let's look at the strategy that you used for one of these brilliant problems. So one of the
Right.
questions was, if we take a full deck of cards with 52 cards and half of them are red and half of them are black, what's the probability that the top one is the same color as the bottom one?
Mm-hmm. So the issue that we had is we were thinking it was
Oh, and our
50%.
multiple choices are 50%, more than 50%, less than 50%.
Right. So we thought it was exactly 50%
Aye.
because we have...
Originally, I did not think that. Originally, I thought it was just below 50% because of just logic. Because I said it was half times half. That was wrong. That was the wrong
reasoning.
answer. But I'm saying, like, my idea was, okay, you have a half, like, on the top. Like, it can either be red or black, right? So if, let's say, you don't know any of the cards, you have a 50% chance of the one on top being either red or black. And now, if you're saying all of these cards are independent, then you're independent as in like in observation, like they're all closed. You don't know any of them. Like it's not conditional on anything. Then each of them have a 50% chance of being either red or black. So I said, okay, for the top one and the bottom one, which is a multiplication of probabilities and intersection, you're simply going to multiply the probability that the first one is one color and the second one is the same color. So what's the probability that the first one is red and the last one is red? 1.5 times 1.5. That was my idea. I mean, it's wrong in hindsight, but
I think
that was my original idea.
I think that would be true if your deck of cards had an infinite amount of cards in it. Because then, like, whatever's on the top wouldn't really affect what's on the bottom.
I guess because it's a finite small number of cards.
Like when we
Or
when we
if we
broke
put
it
the card
down-
back, right? If I flip a card and then I
Yeah.
put it back in the deck
Yeah,
and I ask and I shuffle and I say, what's the probability the next one is the same color as the first one?
Yeah. Yeah, and then we thought about it a little bit differently, saying that if you know that the top card is a certain color, then what are the odds that the other one's the same color? The one on the bottom's the same color. All of a sudden it becomes like, okay, don't think about red and black, but just think about a color, and then how probable is it that you pick the same color? So now all you have to do is analyze what's left in your deck. And you say, well, if the top one is color A, then there are 51 cards left. 26 of them are not that color. And so 25 of them are. So 25 out of 51 is going to be the probability.
Yeah. Yeah.
So only just slightly less than a half.
Slightly less.
But
yeah.
it can seem like it should be a half because, well, there's two choices for the color, right? And if you play this game a bunch of times, it is pretty close to a half. So it's going to be hard to like experimentally decide that it's not one half.
Yeah,
Which makes it a very good
would be nearly
gambling game.
impossible if the numbers are so close to it, right? Like you would sometimes get greater or smaller. Like you would almost approximate it as a half, but be wrong.
Sure.
Yeah,
And
I can definitely see that happening.
we might talk about like, yeah, when Bernoulli is first analyzing, when Jacob Bernoulli, one of the Bernoullis, was analyzing how many times would you need to play this game to decide if it's equal to one half or not. That is another sort of application of combinatorics into statistics, into things about convergence of experimental data to the mean, and all of these numbers of like, hey, if someone says it's 20% likely to snow, plus or minus, or like with a 95% certainty, how are they deciding on those numbers? They are doing a bunch of combinatorics.
So
But
what does...
let's go back to this counting one of dice.
Yeah.
So the way that you counted the top card being the same as the bottom card was you said, what if they're different? What if, like, how many ways can it not be the case? And that there's 26 out of 51 that are not the same color. What if you did this with dice? So if you said, how many ways can you not get a 6 out of 4 rolls?
Can you not out of 4 rolls?
Or maybe what's the probability?
So it would be 20 over 24. Right.
Why is that?
Because on every given roll, you have 5 other choices that would not give you a 6. And then you're doing that 4 times. So you have 4 times 5 options that won't give you a 6. And the total is just 6 times 4.
How did you get this total?
I just added all the possibilities.
Or maybe let's do it with 2 dice. Let's say you roll 2 dice.
Would you
What are the
stop?
total number of outcomes?
As soon as you get a 6, you stop, right?
Sure.
Okay, so then there would be 6. Wait, I don't know anymore. Because you can throw the dice either once and get a 6 and then the game's over. Or you can throw it once, not get a 6, so there's a 5 out of 6 probability that happens. And then you have to throw it again, and then you have a 5 out of 6 again that you won't get it.
Won't get it. But you want to get it, right? So the question is...
So you have like a 1 out of 6 to get it the first time.
So it will be 1 out of 6 to win the first. So the 2 options is either you get it on the first one or you don't get it on the first one, right? And
yeah.
Like both ways if you want to win, the probability to win.
Yeah.
So in the case that you have only winning, then you would do, so then your first situation would be 1 over 6 would be you're winning on the first dice. And then you would add this probability here, which would simply be 5 over 6 times 1 over 6, which is like you lost on the first one and got the second one. But there would obviously also be a subtraction there somewhere, right? Because I'm assuming like if you just keep taking this up, it would at one point get over the limit. So would there not? Because I don't know, you just got in my head about subtracting everything because you can't just add 2 things together. So I'm just thinking about if there would be any intersection between these events. And I know that you mentioned that there might be, right? Like when... No, but you're saying we stopped the game.
You set up these 2. They have no intersection. If you win on the first round, or you don't win on the first round and you win on the second round.
Yeah, there's no intersection there.
But now let's look at the numbers that you got. Because it's not 1 over 6 plus 1 over 6.
No,
It was 1 over 6 plus 5 over 36.
Yeah.
Yeah,
1 over
that's
6
what we
plus
said.
5
Yeah.
over 36.
5 over 6 times.
So
1 over
it's
6.
what, 11 over 36?
So it's 11 over 36.
So
Then
if we
you
want
win
to...
after at most 2. So how many, like, you lose 25 out of 36 times.
Yeah. Wait, does this... I forget, does this game that we set up, this relates to the derangements?
Does it relate to derangements? No.
I don't
It
think
relates
so,
to...
because derangement is only like how many possibilities you can not have it in. a
Exactly, like
position.
how many
This has
ti- how
nothing
many-
to do with that.
How many possible ways can you lose this game?
No, but this has nothing to do with. But it's not like each loss is associated with
Oh, yeah,
like a
that's true.
position in the game
No, yeah,
kind of thing.
no, yeah,
you know,
for
like
sure.
it has nothing to do with that.
I guess I could relate it to derangements by saying for both of them, we're trying to count the opposite. Like we want to know what's the probability that at least one person gets their coat back. But to count that, we can count
not.
what's the probability that no one gets their coat back. So this question of what's the probability we get at least 1 6 when we roll 4 times, instead we could ask what's the probability we get no 6s after 4 rolls.
Well, in this case, you'd only be counting like one thing, right? You'd be saying, well, the probability that I don't get a 6 on any given roll is 5 over 6. And then you multiply that by the amount of rolls that you're doing, right?
What do you mean by that?
Or you multiply it by itself by the amount of rolls that we're doing.
Okay, so you multiply it by itself by the amount of rolls.
Wait,
so
sorry.
there's
have
a
we
5
added-
out of 6
added
chance.
dice here.
So there's 5 over 6, and then you say, okay, I do it once. Okay, 5 over 6 that I don't. Now, what's the probability if I do it again? It's 5 over 6 again. But now, out of the 2 tries, you're doing 5 over 6 squared. Because you're doing it twice. And then if you do it again, then it's cubed. And then 4, you know?
No, but it's not always that, because you also have to, because if you have 3, then you also have to add the fact that you could have, like, you know, lost.
No. As soon as you get a 6, then it's over. You can't roll a 6 and keep going.
Oh yeah, you said that.
Yeah.
Oh yeah, you said that. Oh yeah, they're all, yeah, you're right. You don't-
Okay, so now I go to a calculator and I say, how much is 5 over 6 to the 4? And it tells me it's about 48%.
Mm-hmm.
So I feel pretty good about this game. I will, like, maybe 51.78% of the time, I will win. So here's where the gambling part gets in. This guy who loves to gamble, he knows this game, and he says, okay,
One second.
if I...
Sorry. We have a slight emergency. Oh, sorry.
Okay. Leave this all in.
Yeah. It would be funny. That's funny. You didn't put on Do Not Disturb, man? I did. Oh. Why did it ring? That's interesting. Okay, wait, you have to set it up. Oh, it's not gonna be right. Sorry, go on video. No. Sorry, give me 1 sec.
Now, just me and the editor. How's it going? We're around 49 minutes. If you're...
I don't know why that was ringing.
I guess that's okay.
Okay.
Sorry
Sorry
you
about
were
that.
saying, here's where the gambling comes in.
Right, so here's where the gambling comes in. This is a game relatively easy enough to analyze. Now, let's say someone gave you 2 dice, and they said, I'm going to give you some number of chances to roll double 6s. If you know, okay, I need about 4 chances to get a single 6, and if I had 4 chances, I'm more than 50% to get a single 6. So they let you have 6 times as many chances. They say, I'll give you 24 rolls to try to get double sixes. Is this a game that you want to play? Do you think you have a better than 50% chance to win?
I think you're gonna want to repeat that one time.
No, I don't.
For the audience, I think you're gonna want to repeat that.
No, I heard it. I heard it. It's like 1/12. You have 24 rolls. You're trying to roll 2 sixes on any given roll. I don't think this is a good game. I don't think you want to play this game.
Why not?
I don't know. Just instinctively, I'm thinking you have a 1/36 chance to get it on any roll.
Mm-hmm. And now you get 24 rolls.
We get 24 rolls.
All you need to do is do better than half, right?
Mm-hmm.
And your
So this gambler's logic is, if I need 4 rolls on average to get a 6, then 6 times as many, I should be able to get 2 sixes. Same probability.
I don't think that's right.
It's definitely not right. And this
No,
guy
it's
lost
not.
loads of money in this game. But
Yeah, because
he
it's-
got frustrated about losing this money and sent a letter to some mathematician friends, one of them Blaise Pascal, and said, help me out with this game. I don't understand what's happening. How come I'm losing money? I used to win money in this other game with only rolling 1 die. And this is my logic. Where's the problem here?
Because he's
And
trying
then-
to get the sixes at the same time, which is a lot less probable. Because he was
So how
thinking-
much less? Like, what do you think the probability is?
Okay, we got to work through this.
Because it's not impossible. Like, you try it, you play this game a bunch of times.
Yeah,
It's pretty close to half.
it's close to half.
Mm-hmm.
Okay, well, so let's just say the probability that you don't roll 2 sixes over 24 rolls is gonna be so it's 5/6.
that means each time.
So it's 10/12.
So wait. Remember, there's also gonna be a combination here, because there can, out of these 24 rolls, any of them can't have a 6.
You know,
right?
so okay,
So, like,
the
the first
probability
time-
that you don't roll 2 sixes on any given roll is 35/36, because there's only
Wait, 2
one.
sixes on any given roll?
Yeah, on any given roll, it's 35/36, because there's only one way to get 2 sixes.
Mm-hmm.
So then it'd be 35/36 to the power of 24. That's the probability that you don't roll 2 sixes in 24 rolls.
Mm-hmm.
So then you do 1 minus that, and that's the probability that you do.
So 35/36 to the power of anything would be very high. So 1
Well,
minus
no,
that
because
would
it's
be
less
very
than 1.
low.
It's less than 1. So you raise it to some power, it gets.
Oh, I guess it gets. Oh,
less
yeah,
than
I guess,
one.
yeah. So would it be close to 50? Is what you said?
It's very close to 50. But it's on the other side. So the probability that you lose this game is more than 50%.
Yeah, because again, like 35, 36, pretty big numbers, regardless.
So
Like,
I guess you'd
it
have
just has to be bigger than 0.5. Not
Yeah,
really
no,
point.
but you'd have to play this game a lot to realize that it's less favorable. But if you
Yes.
play it like twice, then you might win twice in a row, and then you're like, oh, this is
Exactly.
easy. Yeah.
And
I mean,
this is
yeah,
how,
I mean,
like,
that's
so
the
many
beauty, right,
Las
of-
Vegas games are set
yeah.
up. Then, like,
where
it's
the
just a very
probability is
small
just-
edge.
We actually did a problem relating. You might have heard of Gambler's Ruin, like a probability problem with like Markov chains, where the question.
Sure. So,
Yeah, where basically we were talking about like what is the probability that an individual who is gambling will lose all his money, or the question was what is the probability that you get to your fortune? Like, let's say you start with 100, you want to reach at 200. Like, what's the probability that you will reach 200 before you lose all your money, right? And like you can actually calculate it, and it's dependent on the probability of winning each and every game, right? So in this case, we have like 35/36 or whatever, or 1 minus 35/36.
It also matters how much you're gambling, though, right?
Also, yes, of course, because no, I mean, well, technically not really, because you can just divide it up. So the way that the Gambler's Ruin problem
But
works
relative to
no, because the way
total
the Gambler's
pool.
Ruin works, it works with adding and subtracting $1. So the idea is it's kind of similar to like a roulette idea. Like you're
Okay.
betting on something, you have a probability of winning, of losing, and the question is, okay, I want to get to this much. What's the probability that I can win? And we actually did kind of a study, and like turns out like if you actually sub in a lot of these real metrics for a lot of these systems, like for a lot of these casino games, like the probability of winning is like literally a smidgen under 50. Like a lot of these games, like we calculated for one was like 0.48, 0.47, but even with a probability like 0.47, if you have like large numbers that you're trying to bet, like we actually did a whole study on it, and the probability that you win is actually very, 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 very tiny, because that's just how they work, right? When the probability is just a smidgen under 50%, in the long term, you lose your money. So that's just how they win.
So what you're saying in this is, even like if we have a game where it's very close to 50-50, but what we want to do is play this game over and over again, and we have a goal of where we're trying to hit, and we also have like a zero where we have to stop playing if we run out of money, we are much more likely to hit zero than to hit that goal.
Well, the question
then-
of Gambler's Ruin is, what is the probability that you reach your goal before zero? So that's the whole question of it, and that depends on the probability, right? So like there's a pretty high chance that you won't reach it. Like if your probability is 50%, there's a certain formula. It's like kind of like a piecewise function. And if your probability is exactly 50%, there's so much chance that you win, depending on what you start with, depending on what you're betting. And if your probability is not 50%, there's this whole complicated thing you plug it into that basically tells you, depending on what direction your probability is in, if you're going to win or lose, or what direction you're going to get into, right?
So this is related to a concept of a random walk.
Yeah, simple random walks.
Which
how
is
we started
saying-
this whole chapter.
When you play a game, you either go up or you go down with certain probabilities. And we want to know, if you kind of pick those at random ups and downs, what's the probability you get to a certain height before you have fallen a certain amount.
Exactly. So like the idea
Or
is
that-
very simple. The idea is like super simple, like it's super understandable, which is why I really like this very intuitive idea, and you can just count it, right? So like
Sure.
in simple cases, of
So a
course.
key part is that you can count it.
Yeah.
And then we have a lot of nice methods for counting. This big complicated formula that you talked about, I'm certain comes from Combinatorics
Oh,
and
it's super
counting
easy to
what
derive.
are the
It's
different
super
ways.
easy to derive. I'm not saying it's a hard formula. It's just like a bunch of like complicated things because it just has a lot of these variables in it. But it's a super easy formula to derive. It's very easily seen that, oh, we get this because of this. Like it makes a lot of sense, kind of thing. You know, and it's all just a very basic probability question, like the Gambler's Ruin. So like it's just something interesting because we were talking about gambling. I just thought it like a random walk can represent a gambler's mindset almost, right? If you think about it.
Is a random walk only like random when it's a 50% chance of going up or down? Or if it's less than 50%
Can
chance,
be
then it's
anything.
not
That's the whole
really
point, right? The
that
probability
it's
can be
more like
anything.
skewed to one direction.
So
right?
the random walk is where the probability is the same in all of the situations. The simple random walk is just when you're going up and down by one. And interestingly enough, any random walk can be converted to a simple random walk just by dividing it by the length of the walk, by the like the length of the chain. So like if let's say every step is like 5, then you can just divide everything by 5 and you make it a simple random walk. And then like a little more complicated version of this, which is what we were learning in statistics recently, was like Markov chains, where it's like instead of having this like the same probability throughout the walk, every step has a different probability. So let's say you're at $100, maybe you think a little bit differently than when you're at $50. Like that's the idea.
Or you go play a different game.
Or you can play a different game, right? Or you can play a different game. Like, oh, once you reach 150, you're going to start this one that has a different probability. And once you reach 300, you're going to go to this one. If you come back down to 150, you might try this one, the first one again. So, like, it might be like a chain like that, hence the name, which is something that we're learning. And I just feel like it's really, really related, especially to what we're talking about right now. Markov chains. Yeah.
So how are random walks related to like just combinatorics?
So we do a lot of fun things about counting. I guess how many different ways are there to do blank, to like walk? One way I might think of it is if you are like standing on the edge of a cliff and you do some random thing that lets you pick a probability to move forward or backward one step, what's the likelihood that you will end up exactly back where you started after some number of steps? And you probably want an even number of steps. But this is also a model of, let's say you make a little diagram where you only go up or down, and you never want to go below where you started. You might consider these like you're drawing different mountain ranges. That you can go up twice and then down twice, and you make a big mountain, or you can go up twice, down once, up again, down twice. How many different ways can you draw these diagrams?
Oh.
It's just funny because like we actually were doing this problem in class, like a couple, like when
Right.
we were learning Markov chains. This is literally what we were doing. Like this is called the return probability of a state. So the return probability of any state is given by some formula, and like you can calculate this probability given by the transient probability. So like what's the probability to move from state 1 to 2? What's like, let's say you've been given this probability matrix is what it's called, where like you have the probabilities to move from each state, and the question is what's the probability that you will return back to this state in n steps, in whatever, right? So there are literal ways that we use to derive, to calculate ways to get back to these n steps. Is that kind of on the line of what
Yes,
you're talking
absolutely.
about? Okay.
It is exactly
So,
this.
like, are you?
I mean, it is
like,
sort
are
of
you familiar
also
with the whole Markov chain thing. Like, is that particularly involved in combinatorics as well, or is it mainly I guess the combinatorics statistics?
yes.
Is it it is. Okay.
Yes. So a Markov chain for listeners is saying, what if the probability depended on the current state, but not on previous states? Meaning, it's sort of like if you have a coin flip, or maybe like drawing cards. You know the probability of getting an ace on the first draw, and then after you've drawn some number of cards, the probability will be different, right? If I don't get an ace, it goes up every time I draw something that's not an ace. So now my probability in these remaining cards is going to be higher.
Really
but
nice
it doesn't actually
example of
matter.
that we actually did in class to understand Markov chains was I think I told you about this, Parker. I think we were talking about it the other day. The frog on a lily pad. This was a really cool basic understanding for basic Markov chains, where let's say there are 20 lily pads around in a circle, and a frog starts on one of these lily pads, right? The frog can either stay in his place with a 1/3 probability, go right with a 1/3 probability, or go left with a 1/3 probability, right? So he can basically just hop from these lily pads. So the question is, you can make any question. What's the probability that he'll reach pad number n in k steps? Is the general question. And in this case, you can think about it as well. In this case, the frog only has 1/3 each time. And a beautiful property about Markov chains, as you were talking about the fact that it doesn't need to remember what it was in the past, and that's that's actually called a Markov property, where it does not depend on the previous states that it was in. So if, let's say, the frog is on lily pad number 18, it doesn't matter what it was doing, what the probability at lily pad number 5, like that. Like, it can only go to 17 or 16 anyways. And even if it could go to 5, it doesn't matter what it was doing when it was at 5. It only matters what it's doing when it's at 18, right? So, like, that's kind of like a simple understanding, which is kind of like how our teacher did it. I don't know if you want to...
Absolutely. I mean, I think of the
agree with
Markov
that.
property as
Yeah.
saying, we don't care where you came from, we just care where you're at right now.
Nice way to put it. Basically summarizing it. Yeah, so how does that have like direct implications? I'm just thinking now, because I know that we've gone through a lot of examples in class, but I just want to hear, especially like you actually, being in a real world statistician, or in a sense statistician, mathematician.
I would not
involved-
call myself a statistician.
Not in, okay, sorry. Who likes numbers? Who likes numbers? How would you say, stuff like these chains and these walks, because we're talking about them, would actually implement in like a real world statistics problem, or like a real world problem, combinatoric, like just a problem?
So an issue that we come up with a lot is that there will be sort of numerically way too many inputs, or like the matrix that we might use might be very big. And if we need to count over a lot of different discrete steps, that we would need to take a huge power of this matrix. So this happens in like weather modeling. Like if you are thinking about how do different particles interact, and we want to make a Markov chain that tells us, is it going to rain tomorrow? Then we need a lot of different, very small, discrete steps, and we need a lot of inputs. And sort of naively trying to compute some probabilities with this means doing an enormous amount of calculations. So what we try to do is reduce the number of calculations. And one way of doing this is looking at like more general properties. What happens in some kind of game state, or what happens in some smaller cases? Can we figure out a rule that will always work, that will give us some accurate measure, and does not depend on doing a huge amount of calculations? So this is where combinatorics comes in. It says, okay, we see this fun problem. Let's try to solve it in general, and then apply what we figured out.
Doesn't that, like, if you try to reduce the problem, doesn't that make your prediction less accurate when you apply it to the
Not
actual...
necessarily.
Oh.
So a nice thing that we do with Markov chains is ask about eigenvalues of this matrix. And that they are telling us something, and we know based on, okay, there must be 100% probability in total that something happens, that you go somewhere. Mm-hmm. So we know already certain, like a vector of all ones has a total sum that is the sum of all the probabilities of going somewhere, which is again 1. So we can find certain properties of the matrix that must always happen, and then use those to reduce how many calculations we need to do.
Well, a fundamental property is that all the columns, I apologize, the rows must add up to 1 because of simply how it's defined, right? Because if you're at any given state, you have to do something. You either stay at that state or you go somewhere, but you have to do something, and that total probability has to equal 1 in some way. And interestingly enough, oh man, I can talk about this for ages, because we're literally learning this right now. Like, it's so cool that we're talking about this, because like we're talking about like, limiting probabilities and how, like, for example, if let's say you start from any state, what's the probability that in 500,000 steps you will reach this state? And the cool thing is,
Ray, I think
it doesn't even matter what state you start. Sorry?
You should have a new episode for talking about Markov chains.
Markov chains is definitely it's definitely a statistics only topic, so it will only be me talking. I can tell you that.
I don't know. I think you can put a lot of physical interpretation into these things, right? If you want to think about how do different particles interact, or what will happen to some electron that you shoot into a metal. It moves around, it hits different things, and stuff happens to it based on what state it's in, and not necessarily what had previously happened to it.
Exactly.
So there are certainly physical interpretations of Markov processes. But that is probably a whole episode on its own.
Were we doing like in thermo? Like, wasn't that something to do with Markov property?
In
like,
thermo? No.
I swear I heard the word Markov somewhere. Not in statistics.
No, I don't remember doing any of that.
Never mind. Because I know random walks occurred. Right? In thermal, we were doing random walks. Very important. Right. Like remind me again. It was like what follows a simple random walk? I forget exactly what it was.
In thermodynamics, I don't remember, but I think we're talking about like gas molecules, and depending on their like thermal energy, right? They'll like the step will be larger.
Something like that we were doing.
And so there's like some distribution based on the temperature of the gas that'll tell you like, okay, the distribution of the velocities of the gases will depend on the temperature, right?
Maxwell, right? That was Maxwell.
That was a Maxwell-Boltzmann distribution.
Maxwell-Boltzmann distribution. It's a little bit of physics knowledge there.
And like something I guess that we can talk about is in terms of counting things. I know like previously we've spoken about macro states and micro states. And I guess I can give a little, because we talked about, we had an episode on thermodynamics, so I guess I can just give a little explanation on those.
Go for it.
So like a macro state is essentially just the general property of the state. And then the micro state is how many ways can you implement this general property. So for example, in terms of gas particles, you can say the macro state of this gas particle is the length of its momentum vector. And then how many ways can a gas particle have this length of the momentum vector is basically all of the directions it can point in. And so to get this multiplicity, essentially the probability that you're pointing in some direction, what we would do is we would divide by the area of the sphere that this momentum vector creates in the momentum space. I will explain this though. I will explain this.
So you're sort of saying
in more depth.
We want to know, okay, for a fixed length, we can think about all the different directions that this might point in, and that builds a sphere for us.
Exactly.
And then if we take a little subset of that sphere, of like, okay, this is like hitting in the dartboard.
Yeah.
What is the probability that it lands in a certain range of directions?
Exactly.
Then we want to compare the area of that range of directions to the total area of the sphere.
Yeah. So essentially, we're trying to count the amount of ways a particle can have that amount, that scalar amount of momentum. And so as the momentum grows, the area of that sphere grows as well. And so there are more ways that you can have this state. So yeah, that's one way that we were implementing combinatorics in our thermodynamics class.
That's interesting. Yeah,
I
was there.
I feel like it kind of doesn't make sense though, because like it makes sense intuitively because it's like, oh yeah, we're doing this like ratio of area, but at the same time, like these discrete vectors, like you're pointing in some direction, but a vector doesn't actually have, like the tip of a vector doesn't have an actual size, and so we're comparing the area of this sphere to something that has area 0. And so I guess what's your interpretation of that, Zach?
So you're saying like the probability that we have a given direction is 0 for any fixed direction.
Yeah.
But we're measuring the probability that we land in a certain range of directions.
Yeah, that would make sense.
And that somehow like adding up all of these individual probabilities that are 0 and we get something that's non-zero is not intuitive. I agree. It's weird.
Yeah. So the way I actually just remembered this, the way that we implemented this into like problems is because entropy is defined as Boltzmann's constant times the log of the multiplicity of a certain state. And so calculating the amount of microstates is the multiplicity of the macro state. And so we'd have this formula for the area of this momentum sphere, plug that into this to calculate the entropy. And then the entropy of a state can be related to, its energy, the temperature, a whole bunch of partial derivatives can give you a whole bunch of other information.
This, I don't know anything about this.
Right, yeah. But I'm just saying, like, this whole, like, counting thing where we're counting these microstates, even though it's, like, this continuous spectrum where we figured out a way to count how many possible ways.
I mean, this is common, right? To make a problem discrete. That instead of saying, okay, there's all of these infinitely many different ways that something can happen, we say, well, what if there was just like a finite number? What if we just make very small boxes and we ask, how many times does it fall into each one of these boxes? So we can think about like the total angles. Well, let's just chop up the sphere into really small boxes and ask, what's the probability that it lands in one of these boxes? And now we have a finite question. And then we can do different finite counting related things.
Which is, I think,
a big benefit of
explained it too, right? Like we brought it down to like a simple finite thing and then generalized it. No,
I don't remember that.
No, I'm just tripping. Okay, never mind.
I don't know.
Never mind. Because I swear, because I think that's how most classes take the idea of like really complicated combinatorics, right? Like when you have these really large numbers, they usually try to generalize it to something like as you were doing right now, Zach. We were saying, okay, let's take 2 cards instead of 52, right? So like common stuff like that, which is what I thought she did, but I might be mistaken.
So like, I was just wondering, what else do you do in a combinatorics class, other than like counting how many ways you can do something?
So one of the big things that we do that's sometimes a surprise is count the same thing twice.
Why?
The why is that it tells us about these 2 different ways of counting. So we did one already, right? Which was we can count how many ways can people get their coats back, how many ways can at least one person get their coat back, by counting how many ways can nobody get their coat back. And we find that, well, one of them is easier to count. Here's a different example. Let's say you want to count, in like a high school discrete math class, you probably see things with combinations and permutations. And you might have seen a combination, so something like 5 choose 2 tells you how many ways can you choose 2 different elements from a set of 5 elements. So if I have like 5 cards, then there will be 10 ways that I can pick any 2 of them, where I don't care about the order of those 2. I just want to get 2 cards. That's 5 choose 2. And if you want like algebraically, this is 5 options for the first one times 4 for the second one, and then divided by 2 because there's 2 ways that I can move them around. If I want to count all of the subsets, so I say I want any subset at all, I can say there's like 5 choose 1 ways to get just 1, there's 5 choose 2 ways to get 2, there's 5 choose 3 ways to get 3, I should have picked 3, all the way up to 5 choose 5. And I've missed, okay, there's 5 choose 0 ways to get no cards. So altogether I know that there's 5 choose 0, that's 1, plus 5 choose 1, plus 5 choose 2, plus 5 choose 3, plus 5 choose 4, plus 5 choose 5. That is somehow counting all of the different ways to pick any number of cards out of 5. So somehow this is some number.
Yeah.
If I add it up, what is it? It's like 1 plus 5 plus 10 plus 10 plus 5 plus 1. So it's 16 times 2, it's 32.
Is it not an identity? Like the sum of n?
Right.
Like,
so why is this an
yeah,
identity?
Wait, explain that way.
Like 100
Like the
choose
sum
k,
of these numbers
k
is
for-
2 to the 5. If I did this
That's
with
what I'm saying.
6
That's what I'm
cards,
saying. There's definitely an identity.
if I add up 6 choose 0 plus 6 choose 1 all the way up to 6 choose
This is
6,
literally how it's defined, man. 2 to the power of, because isn't that the whole thing? Like, yeah. Because like how you count the different number of things is 2 to the n minus 1.
so
Don't you
why?
remember that? 2 to the n.
No, so the first thing I thought of was Pascal's triangle, because I remember doing like something choose something. You just like go down a certain amount of rows and then go into a certain amount of elements. But I don't know why. Like, I guess Pascal's triangle has to do with like binomial theorem, and so 2 to the
Sure.
power of something must have something to do with this whole situation.
Okay, so
of
let me
adding them
count this for
together.
you a different way.
Yeah.
Let me say I want to pick a subset of cards, and the way that I'm going to do it is for each card, I'll decide if I want it or not. It's either in the subset or it's not in the subset.
So you pick a certain amount of cards and you say, or you pick one card.
Well, for
from a
each
certain
card, I
amount.
say, is it in or not?
Okay.
And if I do that for every card, I get 2 choices each time. So the total number of ways I can do this is 2 to the n.
Right.
Or I could say, let me first decide how big of a set I want, and then choose that many. And that will be like n choose k, but I need to add up for every value of k.
But
Both
why
of those
is the-
things count the same thing.
But wait, wasn't it 2 to the n minus 1 though? Wasn't that like I swear that's where I'm remembering my formula though from. Like, wasn't there something like
I
2 to the
question
n
your
minus
memory.
1? Where it was like the number.
Well,
the
we
sum
can
of the
test it out, right? You can
combinations.
always test it out with a small number. So let's take like n equals 2. If there's 2 cards, how many ways can I get any number of them?
So you can get, there are 2 ways to get one of them and 1 way to get 2 of them.
And 1 way to get none of them.
Oh, we're counting the 0?
Yeah, of course. 2 to 0.
Oh,
plus
yeah,
1 plus
of
2.
course.
Okay. So you add 1 to everything.
Yeah. So there's 4 ways.
It's not 3.
So there are 4 ways.
If
Yeah,
you
so it's 2 to
wanted,
the
you can
n.
have 2 to the n altogether minus 1 to get rid of this way of counting 0 things. But we find it really useful in combinatorics to be allowed to have 0 of something.
Wait, doesn't
Say,
that
like-
relate to prime numbers? 2 to the n minus 1? Or am I thinking of the wrong thing?
Ooh. Well,
Oh,
there's
yeah,
a
the
big
question. Is 2 to the n minus. Yeah, that weighs 1 prime. That was a big question, right?
Can we get a bunch of primes that look like that? The
Yeah.
reason that we are interested in that is that we have a nice test to decide if those numbers are prime or not. So those happen to be like the largest primes that we know, just because we have a really good way to check
Oh, yeah.
if they're prime or not.
Also, I was thinking 2 to the n minus 1 because you usually don't count the 0. Because usually, like at least in this situation, like you're not counting the ways to get none of them because you're counting the sum of all possible combinations to get cards. So that's okay. Maybe that's why my brain was going there because I remember.
But that's fine. I
that
mean, it's the
formula
same.
somewhere.
You
it's the same.
remember
thing.
the
It's
same
just,
thing.
Because I'm like, it's just a 1 that's differing, and I'm like, the only thing that's a 1 is just choose 0. So I'm like, maybe that's just not it. Yeah, I think that's just the added thing there.
So this is a way of proving this identity. That we can say, let's count how many ways are there to get some number of cards from 0 to n. And we count it in 2 different ways. We can count by saying, okay, each card I'm going to decide if it's in the deck or not, or in the set or not. Or I could say, let's pick some number of cards, and I'll count all the ways to get that number.
Oh.
So this is what we would call a combinatorial bijective proof. We're saying these 2 things are equal because they both count the same thing. And then we have loads of fun doing this.
That's interesting.
So what you do with this information is like you set up one problem that it seems like you should be doing it one way, but then you say, no, I can count it the exact same way, but using a different method. And then you do it that, and it's supposedly easier.
Absolutely. Not even necessarily easier, but it gives us a different way to think about it.
Yeah, different way. I don't think it will be easier.
Well, the reason why you would do it.
I mean, you could do
The reason,
both ways,
yeah.
though, right?
One thing is going to be
one thing is
easier
gonna be
depending on the
easier.
situation.
One thing is
you're
going to
in.
be easier. The other one's going to be harder. So you can choose to do that one too.
So wait, the reason why the sum of n choose k for like over all of the k's, I think, the sum is equal to 2 to the n, is because for each, like there are n situations where you like say, oh yes, this is in the set, or no, this is not in the set. But why are there n amount of decisions to be made?
So there's n objects.
But that would only be going through them once, right? Because aren't you picking, you're picking, like you say, I want to pick out 4 cards. Then you would be doing it however many times. And then you say, now I want 5 cards. And you'd be doing it again. But
So let's say I just have a set. I don't know how big it is.
Yeah.
I know some things are in it and some things are not. So if I went through the deck one time and I said
get it now.
in it, not in it, then I
Okay.
exactly get that set.
Right. Okay. Yeah.
Another way that people think about it is in terms of binary strings. That if you write a string of zeros and ones, and the zeros indicate like don't include this element, and the ones indicate do include this element, then the total number of strings that you can get is 2 to the n.
Mm-hmm. Yeah, I think the reason that I understood it is because every one given string that you get will be a part of some, like, I don't know the terms, like when you do like 5 choose 2, the amount, like you're choosing 2,
A subset of size 2.
sure, so that subset of size 2, or let's say size k, will show up on any given trial where you're doing like 2 to the n. One specific string will automatically be a part of some k size subset, because that's just, you have n amount of objects, and so if you're doing every single card, then yeah.
Absolutely. So a big thing that we do is things like this, where we try to count one thing 2 ways in order to give a different perspective, or like give an identity between 2 different sums that seem unrelated.
So is this a math class? Because I don't think it's a stats class, right?
It is
It's
a math
class. Interesting. So, because I swear there's a statistics combinatorics as well. Is there not? Am I mistaken? Or are you not aware about the
I'm not in the
statistics
stats department.
Yeah.
I don't know what courses they do. I just know the course that I teach.
Yeah, of course.
And if you want, the textbook that we use is free and open source, and I think is really nice. It's called Applied Combinatorics, and it's by Keller and Trotter. So you can find it at, maybe I should have looked up the name of this thing.
We'll find the link. We'll put it in the description.
But
we'll remember.
That's really
Perfect.
cool. Oh, we have to remember.
We'll remember.
Wait,
We'll
one
remember.
second. We have to put something else in the description too.
Yeah, it was your 52 factorial.
52 factorial, baby. 52 factorial.
Write it down. We'll remember.
I'm writing it down right now at this moment.
Yeah. So yeah, if anybody who's listening wants to go and learn from this open source textbook, which I love getting all these open source textbooks, because whenever like I have a question for myself, I'll literally just go and look through and be like, oh, there's a whole chapter about this in this textbook. So.
Like, there are a lot of things available online.
Yeah.
There are
Yeah.
a lot of things available on the internet.
I know a lot of U of T like material is open source and just online.
Because, I mean, I don't think people have anything against education, man. Like, learn the material, Like, learn it all you want. I mean, as we said, I think in the last episode itself, literally you show up to Toronto, just hop in to one of the
that's
to one of the
true.
lectures, and you can just sit down.
I don't know, like, I guess you would know, Zach. if you have a class and there's like 150 people in the class, you won't notice if there's just somebody that shows up.
How would
that
he even
just,
know that it's not U of T? Someone can just bring a
Yeah,
bag and
no,
he can just look like
no.
a
What
kid.
I'm saying is like if some random person off the street just comes into the class and sits down, like they can just.
I mean,
sit in
during
and learn.
COVID, people who are not university students can't come to
No,
campus.
for sure. But I mean, like, without COVID,
Yeah, this is like
people
a
can just like show up because all the doors are open, right? Like to every class.
The point is that education is free. That's the point. I mean,
Well,
the
education is not free. This is a big problem.
What I mean is like the actual act of learning can be free. The act of education, I guess, yes, you're right. Of course, it's not free because you need that degree, which is obviously very expensive.
I mean, you don't need the degree. You can
Well,
learn
you're
without
right.
getting the
I
degree.
guess you don't really. But what I'm trying to say is to learn
certification.
isn't necessary. But it's not necessarily. You don't necessarily have to put a price to it. It's just what everybody is doing. Like everybody goes to university because that's the thing to do. But I think there are better ways to learn material and not necessarily be in a university. I don't know. There are other ways.
If someone emailed me and said, I would like to audit your class, which means they don't officially enroll, but they do attend, and maybe they do some problem sets, they solve some of the problems, they interact in certain ways, I would say, of course, you can absolutely audit this class.
And would there be a financial obligation to that individual? You're not saying there would be no money involved.
It generally happens where people are in advanced degrees. They have they're doing a master's in statistics, and they might say, "Oh, I didn't get this background information in Combinatorics. Can I take your course?"
Yeah, I actually need to do this for.
But that it's not something that they can get credit for, because it's maybe an undergraduate course, or because they're not allowed to enroll in courses outside of their department. But I think mostly people would say, yeah, of course you can come.
That's amazing.
There are definitely restrictions if there's something like a relatively small class where you can't actually fit more people in.
Of course.
But certainly, and I mean, I try my best to make more things more open, but I know that that's not universal and is very much a lot of pressure from academic publishers to use their expensive textbooks. They sent me a couple when they found out that I was teaching this course on combinatorics.
How do they find
one of them,
out?
Yeah, what? That's
one of them,
creepy.
Oh, because it's publicly listed, right? You can learn.
Yeah, I'm thinking there are actually people looking
things
for
are
who's the next professor
So-
for this course.
They just mailed us these two new textbooks that cost, I think one of them $80 and one of them $140.
Wow.
And said, "Oh, were you interested in having your students use these books?" And I think the books are really nice, but I'm not interested in having these expenses.
Like you're
So,
paying
there is a lot of
$9,000 for
pressure.
school. How much more do you want? Yeah.
9 is even low.
No, I
Our
guess.
international students pay much
Okay,
more.
yeah, I shouldn't say that. No, but I'm saying, shouldn't there be, in my opinion, especially with like a textbook company, I think there should be like some kind of relationship with the school where they're like, we're gonna give these to you for. I mean, obviously, like the school would pay them from the tuition, but like they wouldn't get money. Like you wouldn't have to pay per book. Is what I'm trying to say.
Absolutely.
Like,
so
that would be the goal.
I would
I
love
don't
that
know
this
why
would
that
be
isn't a thing.
happening. And especially would be happening with different ed tech related things. Like maybe you are using something like Top Hat or other software where
like
the
Wiley.
students have to individually pay, like Wiley Plus exactly
Yeah, we
is
literally
this
had to
kind of
pay
a
for that,
scam.
and we couldn't not
Yeah.
pay for it.
Literally, because
It was literally a requirement.
Our problem sets were done over Wiley, and so if you didn't buy it, you couldn't get a grade.
So it was literally like $75 times like how many of our kids were in the first year physics program is how much they
Right.
made just for
So-
because we just had to or we're just not in the class.
This is an enormous industry, right? Of like exploiting students who have no other choice but to pay for this thing. And that is where textbook publishing, academic publishing, a lot of ed tech related things know that they have this captive audience, that students have, like they are required by the universities to buy the textbooks or to pay for Wiley Plus or whatever it is, and that they will do it. And that means that the prices are exorbitant, that the university literally does not care what the costs are. because the students will pay it.
Yeah, this university doesn't have to.
And this
do
is
anything.
an exploitation that I want no part of. So I make it so that all of our courses are freely accessible. Having paid the tuition, that should be all that you need to pay.
Mm-hmm.
But that's not universal. That's not a thing that is required. I mean, it's definitely not required, but it's not a thing that people are doing. So I really support this like movement towards more open educational resources.
Mm-hmm. Especially because some of the top universities in the world are posting lectures and materials on YouTube and just online.
MIT OpenCourseWare is amazing.
Yeah.
Even Stanford has your Leonard, what's his last name? You know what I'm talking about, the old guy who teaches quantum mechanics. Or sorry, general relativity.
He teaches all.
But he's mainly in relativity. He has a lot of stuff in relativity, and like there are so many courses available online. Oh, my phone. There's
So
so many
if you have
courses
some
available.
suggestions of nice ones that people can use to learn more, please share them in this episode description or in the comments.
Oh,
100%.
for sure. I mean, let us know. We love to watch this stuff. I think one person actually sent us an email. Again, we will respond. We actually saw some of them, but we just forget to respond sometimes. Just a lot of stuff. But like we do check them out. So like if you see anything cool, shoot it our way. We're always very happy to indulge in those.
Well, Zach, thank you so much for coming on the podcast again. We had a great time talking
Welcome. It's my pleasure.
about counting things. And
Counting things, I think, is a very, very nice way to put what we spoke about today. Basically, we just counted different ways of thinking about things, which I really liked. You know, there's so
And you
many
have a
ways
couple
to
of
think about
puzzles
the
you
same
can think
problem.
about.
Yeah.
yeah. Oh, yeah. I'm going to search up that derangement problem. Yeah.
There's literally a brilliant
Yeah.
thing on it. So, like, if you literally just want to go for the content and do some practice problems, we can do that too.
Well, awesome.
Is there anything else we want to mention before we wrap up today's episode?
I think that's everything.
I think that's everything.
Okay.
Beautiful.
Perfect. So, yeah, thank you so much to everybody for listening. Make sure to follow us on Spotify, YouTube, or anywhere else you're listening to this. This has been episode number 91 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.